Hi, this is an example of a projectile motion problem. These type of problems are two-dimensional kinematics problems and they require the use of vector mathematics. Pause the video for a moment and read the question there so you see what we're asking. Now, all projectile motion problems, as long as we're ignoring air resistance, which we will always do in this class, these are always going to be constant acceleration problems. And because of that, we can use the similar approaches we did in chapter 2. The difference here is we've got vectors that we need to deal with, and we need to figure out the vector components before we use the equations of constant acceleration. So I'm going to go ahead and write down a chart here that allows us to visualize and record our data for the various vectors. So here's the table we can use to organize our work. Notice that we've listed the 5 variables here, and only the first 4 are vectors, while the last one, delta t, is a scalar. And so only the vectors have components, x and y component columns, whereas the scalar delta t, it's the same number to be used in the equations for either the x components or the y components. Now, when we're doing projectile motion, some of the information we know immediately, and that's the acceleration, because in projectile motion, the acceleration is the acceleration due to Earth's gravity, and that is always a vector that just points straight down. So if we draw the acceleration vector, it's going to look like this. Straight down, and this is equal to the acceleration, and we know what that's equal to here. It's got no direction in the x direction. So if we're to go ahead and draw a coordinate system for this thing here, you can see that it's only in the y direction. So the x component of the acceleration is 0. In the y direction, we see it points down. It's negative, and we know that it's equal to 9.8 meters per second squared. So we already got 2 of these. Now we're going to try to figure out the rest of these. The way that we do that is going to be by drawing a picture of the trajectory and drawing the vectors on there. So here's the jumper, right? If you actually trace out the motion here of this person, it's going to be a parabolic trajectory, kind of like this. And we want to identify the start and end points. In this problem, we are beginning here. So this is your start. And here we're looking at when it reaches the maximum height. So it's about right here maybe. And so we'll call this the end point here. Now we want to draw some of these other vectors on the picture, like v initial, for example. So the initial velocity is a vector that's always tangent, that is aligned with the curve at any particular spot, and the initial velocity goes with the start position. So there's your v initial vector. And the final velocity, right, that's the instantaneous velocity at the end point. It's tangent to the curve there, which is flat on the top, so it's just a horizontal line. Let me draw that a little better. So there's your v final, and I haven't put an f on there. You can if you like, but we got a lot of subscripts for the x's and y's, so I'll leave that off. Now we want to try to figure out if we can know something about those vectors. Well, we are told some information here. So the long jumper leaves the ground at an angle of 20 degrees above the horizontal and with a speed of 110 meters per second. What does that refer to? Well, that would be, if we look at that initial velocity vector, that's the initial velocity specified as a speed, which is the hypotenuse of the initial velocity vector. So this is going to be 11 meters per second along the arrow. And the angle above the horizontal, what's the horizontal? That is a flat direction. And so we're looking at this angle here, and that is given as 20 degrees. Now to figure out the xy components of that vector, we're going to need to go ahead and plot that vector in its own coordinate system and do the math here. Now I've plotted the initial velocity vector at the origin of a coordinate system, and I want to identify what are the x and y components of this vector. V initial y, V initial x. And we know what the magnitude is. That's the speed. That's the hypotenuse, 11 meters per second. And we know the angle is 20 degrees. Now we're going to go ahead and figure out what are the V initial x and V initial y components here. So let's go ahead and write those down right over here. V initial x equals V initial y equals. And we'll use our vector scales to determine this. So we notice that this is a first quadrant vector, so both of these components are positive. Next, we put the hypotenuse, the magnitude, in. And finally, we're going to look at the trig function for the angle 20 degrees. It looks like the x is the adjacent and y is the opposite of 20. So we're going to, for x, we're going to use cosine of 20 degrees. And we'll use for y, sine of 20 degrees. And now we'll calculate these and put them in our calculator to get the answer. So those are the answers we got, and now we're going to put those in the appropriate column for the initial velocity. Now I want to show you one mistake students make a lot, so you don't make it yourself. A lot of people will do this. They'll write the magnitude here and here. That's not correct. It's these guys that go there, right? So we'll go ahead and put the right numbers in there. So the initial velocity in the x direction is 10.3 meters per second, and 3.76 meters per second. And it's smaller in the y direction because the vector arrow, it's closer to y than it is to x. All right, now let's look at something else that we can figure out about the final velocity vector, all right? We're going to go ahead and plot that guy as well, and we'll go ahead and figure out its component. So let me draw that final velocity vector in a graph real quick. So here's a graph, and we're going to go ahead and plot the final velocity vector exactly like it looks in the picture, and there it is. And this one, actually, we can see this is an easy one, right? We know immediately that the final velocity vector for v y, well, let's write them both down. It's going to be 0 because it's only along the x-axis. And can we figure out what the x-axis value is? Well, let's see if we can do it. That's 0. Now notice here that in the x direction, the acceleration is 0. That means that this never changes here, the velocity. Same, because there's no acceleration. Therefore, Vx is still equal to 10.3 meters per second later. So at this point, we've visualized the work here, and we've gathered as much information as we can. We've used our vector math to figure out what components we know. And if you look at these now, we can see that we have 3 values in the x column, 3 values in the y column. In reality, we've only got 2 unique values in the x column because these guys here are the same. So we still can't solve anything there in the x column. However, in the y column, we've got 3 distinct values, and we can start to solve for whatever we want there. In particular, in part A, we're asked how long has the jumper been in the air? We're going to solve for delta t. And remember, delta t is a scalar, so you can use it. The same value is true for the x or the y component. So let's go ahead and solve for that. To solve for delta t using the y components, we're going to go ahead and pick the correct equation that we can use, or a equation, from the list of kinematic equations for constant acceleration. Now these same equations work, but they should be considered only for components, either the x or the y column. We're going to use the y column, and so we can still use these. I'm going to go ahead here, since we don't know delta y, I'm going to consider this equation here, and so let's write that down, number 1, and use that to solve what we're looking for here. So equation number 1, and that's equal to V final equals V initial plus A delta t. And now to use these equations, they're component equations. This is the y direction. All we do is we put a y by each of the variables. And so in this case, we know some things. If we look at our data here, we have a 0 here for y final, so that's gone. And then we need to go ahead and solve for a, right? So if we rearrange this, so for delta t, if we arrange this equation, a y times delta t, is equal to v initial y, and then finally divide both sides by a sub y, we'll get delta t is equal to v initial y divided by a sub y. We're going to put our values in here. So for the v initial y, we have it equal to 3.76 meters per second, and that is going to be divided by a negative 9.8 meters per second squared. And I'm going to get a negative time. I must have done something wrong here, right? Let's see what we could have done here. Oh, yep, bad algebra, right? I needed to move this guy to the other side to write this next step. And so in reality, I should have had a negative sign here, right? Which means this is negative. And the negative sign, that cancels out, and okay, we're good. We're going to get an answer that makes sense, that's positive. And so I get 0.384 seconds, right? And so there's your answer for part A. And we can put that into the table here, 0.384 seconds. Part B asks us, what horizontal distance has the jumper jumped? So keyword here, horizontal. That means left to right, and the horizontal distance is this guy right here, delta x. Vertical distance would be delta y. So we need to figure out delta x. Here's the good news. Now that we know the time, it applies to that column as well as that column. So the time is a special variable in this sense because the same number applies to both the x and the y components. If you don't know it in the know enough variables in the x component column, solve for delta t from the y component column as we just did, and then you can use delta t in the x component column. So let's choose an equation that we can use to solve for delta x, knowing that we have delta t. Let's see here. It looks like there's a lot of different ones we could use. Let's try the third one. So to do part B here, we're going to use equation number 3, and that equation is delta x is equal to v initial delta t plus 1/2 a delta t squared. And again, we need to put x's by all of these vector components. And in this problem, we know that ax is equal to 0, so that whole term is gone, and then we're left with something simple for delta x. Delta x is equal to v initial x times delta t. Let's plug our numbers in and get our answer for delta x here. So going back up to our column, we see that v initial x is 10.3 meters per second. And the same time we got for y is used again here. So let's put that in there. We'll calculate the value for delta x. And the calculator tells us that delta x there is 3.96 meters. Okay, finally we've got one more question we need to answer now. What is the jumper's speed at the maximum height, recall? So we are looking at the magnitude of the velocity vector, right? So here's your velocity vector, final velocity at the top. Speed is just the magnitude of that vector, right? Or we can write it like this. Either way, same thing. So let's look at the final velocity vector. Here it is. And so remember, we're going to use the Pythagorean theorem. In fact, it'll be easy because one of the values is already 0. So to calculate the speed for part 3, we're going to go ahead and do this for part C. So speed at max height, v is equal to square root of vx final squared plus vy final squared. That's equal to, remember that v final y is 0, so all we need to do is calculate this, and vx squared we see is equal to 10.3 meters per second. If we square and we square root that, we're going to find out that v is just equal to 10.3 meters per second. And you can see that when one of the components is 0 for any vector, right, then the magnitude is just going to be equal to the absolute value of the other component. So there we have gone ahead and got all the answers here for this problem. and you can see the methodology of us solving this problem.